everyone. As Marco just said, my name is Matteo Matteucci. I'm from Politecnico di Milano. And today I would like to talk about data generation as one of the way to overcome data scarcity. A little bit about me. My main research field is in robotics perception. So I deal with the physical object interacting with the environment. And because of this, it turns out that acquiring data is often painful. And if you do research in agricultural robotics, it can be also dirty. And I mean, you have rain and all these kind of things. So yes, we deal with data scarcity. But I'm on the stage, but I'm not alone. I would like immediately to thank Eugenio, who works with me on the topic of data generation. So, I mean, this is, you will see me, but we are both on stage somehow. And the main research interest of our lab are in machine learning and deep learning. And recently on generative AI. Now, when I say generative AI, I mean, you immediately think about these kind of things. And it is actually what we are interested in. Indeed, you have a potential of generating images out of noise. And this is what we will love in order to increase the amount of data that we have available. Now, these two are just two examples, but the history of data generation has a long history. This is an example. I would like to make this session a little bit interactive. Please raise your hand if you think that the real image is the one on the left. One. Oh, okay, don't be shy. Good. Raise your hand if you think that the real image is the one on the right. Half and half. Well, first of all, no one of them is real, obviously. But this is the goal of generative adversarial network, being able to generate images that they look so close to reality that actually an expert is in doubt. I mean, half and half. I don't know whether it's real. I don't know what is not real. In this case, you played the expert, and we basically made the first round of a generative adversarial network. And you can have a very simple architecture to generate these kind of images. You have two neural networks. One is the generator, the one that has generated those images. And the generator has the role of taking a sample of noise and generating a possibly real-looking image. And then you have another piece of the model, which is relatively simple. It's the one you have played 1 minute ago, which is the so-called discriminator. And the role of the discriminator is to decide whether the image comes from real distribution or the distribution of real images. So the goal of generative adversarial network is to structure the space of noise such that images are nicely placed. And whenever you sample from this data distribution, you sample an image which is possibly real. I mean, you can think of sampling these two pictures that we know by heart by now, but also these pictures. They are just another sample from this data distribution, which has been learned by this network. Or you can sample these two people from the very same distribution, or, well, these two people. Now, generation is not perfect. There are subtle errors, some small errors. So one typical error is with the ends, or at least the initial models had problems with ends. With glasses, you see that at some point glasses just disappear. I mean, the problem of the original generators was on generating symmetric figures, generating consistent, I would say, data, especially for articulated parts. But this doesn't mean that we cannot train with these images. I mean, they're still good. There are other kind of images. Usually they have a problem with fur. I don't know why. They tend to grow hair everywhere. But I mean, this is not a problem. I mean, if you're interested in cats, this is perfect. I mean, you grow hair everywhere, and these are perfect cats. Obviously, also, these cats do not exist. Not even these sneakers. I mean, they do not exist. So the key point is that if we have a way to structure the latent space, I mean, this distribution, such that we can sample, we can generate new data, possibly an infinite amount of data, and then we could overcome the data scarcity issue, which is our today goal. Now, how, by the way, also these nights do not exist. So it doesn't work just with the, let's say, small items, small industrial item, but it works also with context, with scenes, and you're able to generate this. Now, how can we sample images that do not exist? Let me take this nice example from the literature. So let's assume that by means of our generative adversarial network, we have structured the space such that our data set has been properly ordered and structured in this nice, supposedly Gaussian distribution. We will start from an image, and when we move from that image to another image in the same space. So, I mean, we can morph the image, and obviously this one was not in the original data set, is somewhere in between, but it makes sense. I mean, and the more you move, it makes even more sense, and the more you move, it's getting closer and closer to the other image, and I mean, eventually it will reach the target image. By the way, all the images in the middle, they do not exist. And these are new data that could be used to perform our task in case we have, yes, structured properly our embedding space, and we have, let's say, the possibility to sample from that space. I mean, this works with nice images and cartoons and, let's say, reasonable performances are expected, but how can we leverage these capabilities? How can we use a generative model to generate data set? So let's assume that we have structured our space, and in the previous case we had a single labeled data set with only faces, with only sneakers, with only teddy bears, with only houses. In this case, we have another example where you have, in the embedding space, you have put object, 3D objects. So you can sample 3D objects, you can sample 3D models, or you can do it with molecular as well. So, I mean, we have seen a lot of biotech and biodata today. This morning there was the keynote speech, which was on how to use AI and deep models to solve, let's say, chemical problems or problems in chemistry. So now that we know that we can get some data, we can generate more data, possibly many of them. Can we leverage these for training? Would be possible to reach the same level of results compared to the original data. I will not play the real against fake with this slide. The one on the left are the real one. The one on the right are the synthetic one. No way to distinguish them. But the good thing is that now we can generate thousands of these, and we can even generate samples that are slightly different from the one we have trained our generator. So the question is, let's assume we have some real data, and we are interested in developing a classifier, and then we will evaluate eventually this classifier. What if, and we know that we can get good results, what if we get real data, we train a generator for this data, and then we sample synthetic data to train the same classifier, and then to get eventually the same result. This is good for a series of reasons. It's good because in theory you could get an unlimited amount of data. It's good because if your data have some privacy issues, think about an example of people. I mean, if you can train with people that do not exist, I mean, you solve a lot of problems. And also exchanging data, if you exchange a generator, not the data, I mean, it might solve some of the issues. However, it has been observed that this has quite good performance. So it looks like you cannot exactly get the same result of the classifier on the same data. And we have done some experiment of this by looking at the classification accuracy score, which is the accuracy of a classifier trained on data which have been purely generated. So you read a lot of papers, you read that they tend to mix up. I mean, you have real data, you build the generator, you mix and match with some generated data. What if we throw away the original data and we train only on the synthetic one? So turns out that there is still a gap. So, I mean, very simple data set for which you would expect to be able to train a generator which is quite accurate. And if you look at the data that have been generated, they look indistinguishable from the real one. And you see significant gap. I mean, in the Derma-MNIST over there, you have a 10% difference. On the Cypher 10, you get even up to 20 almost % difference. So there is still a real gap between a baseline, which is your classifier trained on the original data, and the real data, and the baseline, which is the classifier that you train on purely generated data. Obviously, we are not the only one working on this subject. There has been some work by Dutt and others which have tried to improve this with a lot of techniques. Usually this is done by not just sampling, but selecting the samples. I mean, you generate a sample randomly, but then would this be useful for the classification task or not? Because so far we have trained the generators in order to make images that they look the same at a human perspective, that they look like real, not because they are useful for classification. I mean, in the raise your hand, close your hand, I mean, there was not, would this be useful to understand if? It was just, does it look real or not? So we started working on this with the idea of filling this gap. And we developed a technique, which is called gap filler, GAFI. And the idea is not to retrain the generator, is to post-process the data acquired from a generator, maybe by resampling with a higher variance in order to explore a bigger part of the embedding space, or by sampling and discarding based on the usefulness of that sample to train a classifier. And if you do this with multiple generator, we have seen that you can have multiple generator for the same task. You see that you're able to get quite close to the classifier trained on real data. Did we reach it? No. Well, not yet. I mean, we have been working with the generative adversarial network. There is still an open question whether we will be able to defeat a real data and just to train on real data. Maybe new models which have been trained by the denoising diffusion probabilistic model might turn out to be more effective than generative adversarial network. But more important, they are already there. We have huge models that have been trained on large amount of data. We have huge models that now we call foundation models that we can interrogate, we can query for data. We can query for data, and then we can apply the post-processing techniques to these foundation models in order to increase the diversity or to retrieve data which are more useful for classification. A lot of questions, no answer, except one. Nice, foundation models, impressive result, but still one motto holds, and is the usual one: garbage in, garbage out. Thank you very much.